Hey everyone, I'm Jason Yee. I'm the director of advocacy at a company called Gremlin. But today I really wanted to chat about how we essentially step our way into resilient services. And I think we can do that with this concept that's been called the adjacent possible. Biologist Stuart Kauffman created this theory of the adjacent possible. And without getting too deep into the science, the gist is this, that the theory is that evolution builds upon itself. For example, a fish cannot directly evolve into a land animal. That's impossible. But there's all these things that need to come together in order for that to happen. First, the fish needs to grow lungs and the ability to breathe air. And then the fish needs to grow thicker bones that help support its weight outside of the water. And then those bones, those fin bones, need to turn into solid bones for legs, right? And have a joint in the middle for elbows. And the ends need to morph it from fin into feet. And in hindsight, we can see this entire chain. It all makes sense to us. Of course, these are the natural steps that need to happen. But moving forward through time, they don't have that ability. It unfolds. Each step is only possible after the previous evolution and couldn't be conceived of before then. And so in his book, Where Good Ideas Come From, author Steven Johnson applies this to innovation. Just like the evolution of the fish to a land animal, you can't immediately jump from the invention of, say, light bulbs to lasers. There's all these things that need to happen in between. The invention of the light bulb creates a platform where innovative people can begin to imagine what's next. Things that they could have never imagined had they only had fire or candles. And so Steven Johnson explains the adjacent possible as this. The adjacent possible is a kind of shadow future, hovering on the edges of the present state of things. It's a map of all the ways in which the present can reinvent itself. And he goes on to further describe it as this: the strange and beautiful truth about the adjacent possible is that its boundaries grow as you explore them. Each new combination opens up the possibility of other new combinations. You can think of it as a house that magically expands with each door you open. You begin in a room with 4 doors, each leading to a new room that you haven't visited yet. Once you open one of those doors and stroll into that next room, 3 new doors appear, each leading to a brand new room that you couldn't have reached from your original starting point. You keep opening new doors and eventually you'll have built a palace. So as I was reading this, it got me thinking about something that we talk about all the time, and that's contributing factors. We say this word a lot when we think about and talk about incidents. We often say that in complex systems, like the ones that we work on, there is no root cause. It's not just one thing that leads to incidents or outages. It's just contributing factors. And that one factor allows for another thing to happen, and then combined with another factor, it all leads to our major incidents. And we often talk about this as if it's all black swans and we could have never imagined it. But it got me thinking that if failure has contributing factors, that maybe there's an idea of the adjacent possible of failure. And what I mean by that is that in our current understanding, your current understanding of your system, you can imagine possible failures. But it's extremely difficult, if not impossible, to imagine the catastrophes that those possible failures would lead to, how all of those collaborating factors can come together. And this naturally leads me to think about the 3 categories of knowledge and unknowns that we have. And the first is the known knowns, things that we know, right? It's pretty obvious. We all know a lot of things. And so these are the things that we know. We're certain about them. And then there's the known unknowns, the things that we were ignorant of. We know we're ignorant of. For example, I know that nuclear submarines exist, right? Our Navy has them, people work with them, but I also know that I'm completely ignorant of that. I have no idea how to operate a nuclear submarine. That's a known unknown. And then we have unknown unknowns. And these are the things that they're so foreign to me that I don't even know that I don't know about them, right? There's maybe something crazy. There's some UFO or something in Area 51 that I could never imagine. And so I don't even know what I don't know about it. And if we put this into Johnson's analogy of the rooms, the room that I'm currently in, that's my known knowns. I can see everything in that room. I know about it. And the adjacent room, that's the one that I can imagine, right? I see a door and that door leads somewhere and I can imagine that being a room. So that's my known unknowns. I know that there's something there, but I don't know exactly what that is. And in this analogy, then, the rooms beyond that, there are 2 rooms or 3 rooms away. Those are my unknown unknowns, the rooms that I have no concept of. So the question then becomes this: how do you explore those adjacent possibilities? How do we innovate on failure and move into adjacent rooms so that we can start imagining what's beyond them? If we take the idea of known knowns are our non-incidents. They're the place that we're currently at, right? If you know there's a weakness in your system, you're going to build your system to prevent that. And so this is why we design for reliability. This is why we have tests to ensure quality. It's why we've built systems for auto remediation, right? We have things like auto scaling groups that'll note if a VM is down and it'll restart it. Or we have things like Kubernetes, or they can automatically scale them up. And then we have our known unknowns. And this is where monitoring and observability are important, right? We know that our systems need resources. We don't necessarily know what they're at or how they're trending. And so we have tools that we built to track that for us. This is also where we create incident response processes, because again, we know that our systems could have something go wrong with them. And we don't know exactly how that will play out. But we know that we can create processes to respond. We can pull in the information and the people that we need so that we can deal with them when they happen. The problem, though, is those unknown unknowns, the things that are so far out there, the things where the failures, again, become collaborating or contributing factors. We don't know how that'll work. And so we don't have anything. We're not building for those. We don't have processes for those. We only have hope. We hope that they don't happen. So in this, if we're here in our known knowns, how do we move into our known unknowns? And I think the way that we do that is chaos engineering, or at least that's one way, and a way that I've used that I think works really well. Chaos engineering can start to let us explore those known unknowns by reproducing incidents. And when we do that, when we use that to gain information and gain better understanding, then our known unknowns become our known knowns. And that means that those adjacent possibilities become our known unknowns. We start to diminish some of that unknown area. For those who aren't familiar with chaos engineering is often explained this way, that it's thoughtful, planned experiments designed to reveal the weaknesses in our systems. And this is what I used to say a lot of. It's short, it's memorable, it's not a bad definition. It plays into the idea that we don't want weak systems, we want strong, robust systems. But over time, as I've started to do chaos engineering more and help others to do it, I've sort of evolved my description of it, or my definition for it. So yes, it is thoughtful, planned experiments. You have to be intentional about your chaos engineering. If you're randomly going about things, you're not going to be learning a whole lot. And you're probably going to be a jerk to your colleagues who are having to deal with your randomness. But rather than designed to reveal our weaknesses, I think it's designed to improve our understanding of how our systems actually work so that we can improve them. Because ultimately, the best way to make better systems is to have better engineers. Systems don't build themselves, they rely on us. So the better that you are as an engineer, the better your systems are going to be. So how's this done? Well, I like to follow the scientific process. If you remember from grade school, you start with a question about your environment, you form a hypothesis about how you think things work, you test that hypothesis, gathering data, you analyze that data, and then you repeat it, and you share the results. So in chaos engineering, the question often starts as, is my application or system reliable? And with my definition, I think that's the wrong question. I think the question is, does my application or system work the way that I think it does? From that, then, we can form a hypothesis that given some condition, some sort of failure, how do I think my application is going to react? From there, we just simply inject that failure, or we replicate that condition, and we gather the data. As we gather that data, then we can analyze it, and we can learn from it. Or in the case of the adjacent possible, we can start thinking, if this failure condition happened, what other contributing factors could come along and lead to catastrophe? Right? From this new platform, I can start to imagine more that I wouldn't have been able to do prior. And then again, sharing and repeating. So sharing your learning so that everybody in your organization can learn from what you've done, and repeating it as you begin to improve your systems and your understanding. When you do this, start small, be careful. Try to start with the smallest experiment that you can that will yield some data, and then grow from there. Oftentimes people talk to me and they're afraid, I don't want to take down production. But I always mention that you do this all the time. You're deploying changes and code to production all the time, and you're not freaked out. And it's because you've built confidence in development, in staging. So do the same with chaos engineering. Start small, start in development, build your confidence. And by the time you're pushing to production, it's not the idea of, I'm going to take down production. It's the idea of, I'm confident and I'm just building more confidence. So back to the question, and I think it's this, is how do you explore the adjacent possibilities of your system? How do we innovate on failure and move into those adjacent rooms so that we can understand more about our systems and how they fail?
So with that, Jason, I think your talk had a really great viewpoint on unknown unknowns, and I guess here's the way that I would frame the conversation, right? I think there is the point of observability is to be able to answer those unknown questions when they happen, right? And yeah. I think sort of the take that I usually hear is, you can never know what those unknown unknowns are. So let's just be ready to dig into them. But it does strike me as a little bit reactive. And so I think what you're proposing is, start iterating your way towards that. But how do you ever know what those unknown unknowns are?
Yeah. I mean, I think that's exactly the point, right? I mean, that's why we love observability, is we get into an incident and we're like, this thing happened and I don't know what happened. So I'm like, I have these questions, right? And I think the problem when we think about like true unknown unknowns is like, you don't know what questions to ask, right? And so that's why we basically are waiting for incidents to happen to figure out what questions we need to ask. And so, there's definitely the viewpoint of, well, that's just the way it is. There's always unknown unknowns. You can never know everything. And obviously that's true. You can't know everything. But generally, I've been doing a lot of study on innovation and practices, and there is this notion that we can start to explore that, right? Like innovation isn't just luck. And I think similarly, if we think about failure, we can't really just assume that it's also luck, right? That it's black swans and catastrophes just happen. And so I found the idea of the adjacent possible interesting, right? That we can start to explore, right? We can start to dive into our systems to try to understand a little bit more and maybe simulate failure with a notion of, yeah, if it's all contributing factors, can I try something? And then from there, imagine what else can happen, right?
Sure. I mean, I'll give you that, right? I think that you're right. It's not just luck, but there is such a permutation of possible contributing factors that come together that it seems like an infinitely large puzzle to solve. And I think you're right. Like to some practical degree, there are bits of that puzzle that we can guess against, right? And I guess, I mean, there's no practical way to answer this question, but how big is that unknown, right? I guess how big is infinity?
Yeah.
And so I guess, how much ROI do we get on that, right? Like it seems like we're investing a lot of time in trying to guess at all of those unknowns and chip away at it. Is it worth it? Are those the real failure modes that we're going to end up seeing in production?
Yeah, I mean, that's a good question. And it's largely to the organization on how much they want to invest. I think part of the reason that I was thinking about this is we often, we've adopted blameless postmortems, Gremlin, and I think everybody has. And one of those is always that like hindsight bias, right? Of people being like, you avoid hindsight bias, but hindsight bias is there because how many times have you been in an incident and you're like, this thing happened, and in hindsight, you're like, of course that happened, right?
Yeah.
And so I think, yes, there's a huge amount of unknowns that we can never know, and you shouldn't spend all your time doing this. But I think that there's enough stuff where we could sort of predict if we'd only put ourselves into a position of spending at least a little bit of time trying to imagine what it might look like.
Yeah.
Right. And I think that's the balance. I
guess, I mean, here's what I hear you saying, right? That, we've mentioned a few times today, how our systems are socio-technical, right? And a lot of the things that you do find in a blameless retro, in retrospect, you're like, yeah, of course that was going to happen because of the teams that we have set up, the systems of communication that we have, some of those social bits. And so you discover that when you simulate a failure, no matter what the failure is. I mean, to some degree, right? Failure can actually float up some of those people problems that you intend to find, right? Do you know the right place to go figure out what is happening with this service, right? When you communicate to someone else about this service, do they have the same model in their mind of how it works as you do, right? And I think those kinds of things, you are 100% right. You will find that when you just simulate there being a failure, to asterisk any failure, like to some degree, right? And so, yeah, I think I see that argument. But what about actual observability, right? And so where's the line? Like where does observability fit into your chaos engineering experiments? Do things need to be instrumented to discover those failures? Are they independent? Do they go together? Like what do you?
They totally go together. If you don't have observability and you're starting to do chaos engineering, that's a losing game, right? Like what are you going to actually learn if you can't see anything, right? So you definitely need to have both together.
I would challenge that a little, though, actually.
Yeah.
Which is interesting as the observability person here, right? Which is, I think, for some of those like socio issues on the socio-technical spectrum, does the observability matter? Yes and no. I think it does help in those cases where, maybe you have different models of understanding the system, and without actual data and a real model to look at what's really happening in production, and it's hard to get on the same page. But for some degree of things where it's communication issues or access to tools or access to production, right? Those things, maybe not so much, but I'm sorry, I hear myself say that, and I think I softened my stance as I did coming into this talk. So I'm curious for you. Let's hear yours, which I sort of interrupted, which was more absolutely you need to have the telemetry. How does that come into play?
Yeah, I mean, that's funny that a lot of this and what I've been thinking about is it's this theory. It's interesting, right? So I don't have it completely set. If that was the goal, so I love the fact that we're talking through this and kind of thinking through this, because that's predominantly what I wanted. And I think it goes also to that chaos engineering isn't just this exploratory thing, right? Sure, you can use it to test systems. A lot of times we use it to run those sort of incident replications, to onboard people to processes in that incident response. So that's definitely a useful value. And in that case, yes, if you're using it for practicing your incident response, maybe you don't need observability. But obviously, this being the observability conference, yes, you should have it, and you're going to get the most value out of chaos engineering.
I don't know. So yes, I hear you. I hear you on that. I think, one model that I'm really fond of when it comes to chaos engineering is running tabletop experiments, right? And just sitting down and talking through, here's what I think this error is going to look like, right? And asking questions. What sorts of telemetry would we need to be able to see that, right? What do we need to communicate to stakeholders? What are the dependent services, right? Things of that nature. And so I think maybe it covers that case, but I think you're also right that there are certain failure modes that you can expect, right? And I think specifically the use case here is maybe new features that we're launching into production, right? I sort of have an idea of what this, maybe new microservice does. It returns 4 possible answers, right? And if that's the case, then sure, we can actually iterate and model a lot of things around those. I think that seems like less of an infinite problem. I think in those scenarios, 1000%, you want all the telemetry you can possibly have to figure out, well, did those failure modes that I expect to see actually happen the right way? Or the way that I expected, right? I think those things can be surprising sometimes.
Yeah, absolutely. The question then is, though, how many times do we have those services that are truly microservices that return that limited set?
So, okay, all right. I hear you, right? Because the problem domain is not always that small, right? And so then where's the practical advice, right? I come back to observability means you have the telemetry and the tools, hopefully, to be able to get down to the root of what happened, where was the bottleneck, where was the source of error coming from, despite all the contributing factors that happen around the incident. When it happens, and then trying to predict that in advance. I guess, what is your practical advice for folks trying to figure out, I guess you have observability in your systems, maybe you're not running intentional failures in production yet, right? Or doing real chaos engineering. How do you start to approach that? What are some practical steps to take to start, combining the two practices?
Yeah. I think starting out, you definitely, when you're starting out, a lot of chaos engineering is simply going to be confirming that what you think is true, right? So that is going to be testing out the fundamentals of does my service restart if it fails? What happens if I cut off network connections? All of that is, definitely start there. Start, as mentioned, small blast radius, start in development, work your way, build your confidence into production. That's kind of the standard core of what we've always thought about for chaos engineering. But I think, in talking about this whole adjacent possible, part of that is cool, if that's the base level, where do we go from there? Where can we start to get true value? or interesting value in terms of what we're doing. It's fine if you're doing chaos engineering and to you it is just tests of like ensure that this thing restarts. Like that's easy, and we've got tons of customers at Gremlin that do that, right? They put it in their CI pipeline, and when they go to deploy and it's running all those tests, that's what happens, right? It kills their process. They wait for it to come back, check that box. Yes, good to deploy. And I think that's a good baseline. I think that as we talk more and more about complex systems, though, starting to explore some of the ways and build our knowledge around our systems and chip away at those unknown unknowns becomes extremely valuable.
So it sounds almost like what you're recommending then is you just pick sort of, I was going to say an arbitrary point, but maybe like a really important point in your infrastructure, somewhere in that architecture, start there, iterate at those failure modes. And then once you sort of have an understanding of what those major ones are, then, with the adjacent possible, right, go to the next adjacent service and iterate there, discover a little bit more there. And then, as you start to, figure out, what are the adjacent properties, how does one service affect the other, then, you'll never have a complete picture, but you'll start just sort of, slowly understanding a lot more of the common failure modes, right? And so the way to get there, one, do the experiments, and two, have the telemetry to understand what actually happened when things went awry.
Yeah, I think it's a good way to sum it up. Is really, start with the things that you generally have more confidence in or more understanding of, build that up, and then start expanding.
I love it. I think that's a great way to go about it. It looks like we're almost at time. So Jason, I want to thank you for your time. Thank you for participating in this talk. And then I want to let everybody else in the track know that we are meeting back over at the main stage for a closing talk. So we'll see you there in about a minute or two. Thanks again, Jason.
Thanks for having me.